Okay, so equating Newton's two laws together, we're literally going to set them equal to each other here. And then the first thing that we see is the mass of the planet is completely irrelevant to the whole thing. That just cancels out. And then we can say then the acceleration due to gravity is just equal to the stuff that's left over on the other side. All right, let's see, over r cubed and our r vector. Now, this is meaning that the acceleration and the position vector are proportional. And notice the negative in front, of course, that's indicating that, in fact, they are in opposite direction, but parallel, which agrees completely with the drawing that we have here, right? So that agrees that way. Oops, need a writing tool. Here we go. So we've got acceleration, then we can say is parallel to the position vector, right? And then we said, in particular, it's also opposite, okay? But vector-wise, that means that these two things, if we go to a cross product, the cross product of these two is zero, the zero vector, okay? So we have the zero vector is the cross product. Well, if you keep in mind here that this cross product is zero, we're going to actually take a derivative that at first is going to seem like comes out of nowhere, but you'll see that it's going to get used in a little bit. We're actually going to take the derivative of the cross product of our position vector and the velocity vector, okay? And this requires a product rule, right? So derivative of position vector cross velocity vector plus position vector crossed with the derivative of the velocity vector. Of course, r prime is the velocity vector, so this just ends up being v cross v, and here v prime is the acceleration vector. All right. And now we've got, look at that, r cross a, which we know is the zero vector. We also have v cross v, but v cross v is a vector cross with itself, so that's also the zero vector. So putting these together, we just get the zero vector. So why did we even bother doing this? Well, the key to this, taking this derivative of r cross v being the zero vector, for something, a derivative of something to be zero means the original thing had to have been constant, right? So in fact, r cross v is a constant vector. And that's the reason we actually did this cross product, was to show that. Let's call this something. Let's call this resulting vector, we'll call it h. Okay, you may say, why h? Just because the notes I wrote up, I called it h, for lack of anything else. Okay, so we'll have to keep in mind when this h thing, we're going to use it, we'll use the fact that it's constant. That'll be useful. Okay. The other thing with h being constant, not being constant, but just h being a cross product of both r and v, that means that the h vector has to be perpendicular to both of these vectors, right? So h has to be perpendicular. In particular, I want to point out it's perpendicular to our position vector. Now, our position vector, though, as the planet's orbiting the sun, the position vector actually changes for various points in time. So not only is it perpendicular to r, it's always perpendicular to r. So you want to think of that as that vector function. It's always perpendicular. Okay. So, going back thinking about cross product and right-hand rule, r cross v with a right-hand rule actually means that this constant vector h is coming out of the screen towards us. Okay, so that's something to keep in mind, that it's actually out of that plane of the screen. Okay, and that's true for all values of t, meaning that the planet must lie in the plane through the origin perpendicular to h. So we've achieved that goal now, showing the planet's always in the same plane.